All right, so yesterday we talked about nucleophilic addition to aldehydes and ketones. Today we're going to kind of reiterate that, so a lot of this will look really repetitive. But let's imagine that we have some sort of ketone or an aldehyde, and we react this with water. Could likely be in equilibrium. And what do you think the final product might look like? I'll give you a second to think about it. So what's going to be the nucleophile, water or the ketone? Water. And then you might have some proton transfers occurring. Does anybody feel pretty confident in what they think the product might look like? A few people? We'll go through and do the mechanism. I was just kind of curious if we could get there without a mechanism. But it looks like this. So this works with aldehydes or ketones. And in this reaction, we're reacting it with water. So usually what we refer to this product as is a hydrate, meaning it has water added into it, right? So a hydrate can mean a bunch of different things depending on the context. Oftentimes you see it in inorganic chemistry. I'm not sure if you remember back to last year, but if you see the dot, something H2O, those are also hydrates. This is just the hydrate of a ketone or an aldehyde. Let's take a look at some other examples. And I just want to do a quick comparison. So in the top example, what's the name of that ketone? Acetone. What's the name of the aldehyde on the bottom? Formaldehyde. So in each of these cases, they can form hydrates. My question for you is, which one's going to form more of the hydrate in solution? Acetone or formaldehyde? Formaldehyde, why? It's way more reactive, right? So that carbonyl carbon isn't stabilized through hyperconjugation. We would anticipate that formaldehyde, meaning this molecule down here, would be a heck of a lot more reactive, which would drive formation of the hydrate. And you can actually measure this in solution. Whoops. You get about 99.9% hydrate with formaldehyde. In fact, you normally can't just buy straight formaldehyde. You normally get the hydrate. And then with acetone, you get about 0.1%. So this really drives home the reactivity difference between ketones and aldehydes. Aldehydes are way, way, way more electrophilic than ketones and form a very appreciable amount of the hydrate, where ketones, not so much. All right, so let's take a look at the mechanism. Yeah. Yeah, so it does get trickier. If you're trying to drive it forward, there are some tricks you can use. So for example, Le Chatelier's principle, flood it with water. You can try to nudge it along. The other thing too is removing the hydrate from solution will also drive formation that way. So there are various tricks you can use to take advantage of Le Chatelier's principle. Do you guys remember Le Chatelier's principle from Gen Chem? Yeah. All right. Mechanism. Let's take a look at the mechanism. And let's do acidic first, just to drive it home. And we'll do formaldehyde, just to keep things simple. And we know the first step in this reaction would be what? Not hydration. Acid-base chemistry is way faster, right? So acid-base chemistry is going to be favorable. And we know we'll protonate that oxygen because it leads to a resonance stabilized conjugate acid, right? Really, it's the best spot we can choose to protonate. All right, and then in our second step, the slower step than our acid-base chemistry, is water attacking in. Okay, so now we're almost there.
Question.
Yeah.
Is it possible for the lone pairs of oxygen to attack and act like acid? Or is that just
The lone pairs of oxygen.
When it's in resonance pair, in its resonance form where you get that partial positive and the partial negative, the lone pairs act on that partial positive and drive this call?
Not really. I think I understand what you're asking, and I think the answer is no, but we can talk about it later.
Okay.
Yeah.
Okay, yeah, I got the product.
All right, and then last step, what do you think happens? Deprotonation. So I'll just write minus H plus. Usually you have excess water that can act as a proton shuttle. And you can reform your neutral product. But one thing jumps out to me about the acid. What's that? It's catalytic. Whoops. So let's make a note of that. Your acid is catalytic. Normally the acid you pick for this reaction is one where the conjugate base isn't a nucleophile because you don't want it to compete with water as a nucleophile, right? So often sulfuric acid, things like that will work well. Tosylic acid, phosphoric acid, the things where the conjugate bases are so big, bulky, and resonance stabilized that they're really crummy nucleophiles are often used. All right, let's do the basic one super quick. All right, so in this one, I'm going to kind of spread things out a little bit. Actually, let's draw out all our bonds in water. And I'm just going to make a generic base B. All right, what do you think the first step is going to be for this? Fastest reaction in chemistry? Acid base. We've got a good base. Where's our best acid? Water. Okay. Oftentimes you'll just use sodium hydroxide to begin with, but you could theoretically use another base too, as long as that base isn't nucleophilic. All right, and then in our next step, we would still have our formaldehyde floating around. And we've got hydroxide now floating around. And we've got our conjugate acid. What do you think will happen next? Hydroxide is our best nucleophile. So we can kick up electrons. Oops, yeah, you're right. It should just be HB, not HB+. Good catch. So now we're almost there. Last step, what do we need to do? Protonate. So we could, in theory, steal this proton back. It really depends on the nature of the base that we used. It's kind of hard to tell in this case. But for example, if this were water, that would definitely be a reasonable equilibrium reaction. So oftentimes in this reaction, you normally just use sodium hydroxide and water. However, in theory, you could use other bases as well. Does that make sense? So the same thing is true here, where our base is catalytic because at the very end, we spit out our base with the negative charge. So we could just make a note that our base is catalytic. All right, there are some weird examples though that I really quickly wanted to go over. I've been trying to drive home the idea that aldehydes are a lot more reactive than ketones, but that's not always true. All right, so let's take a look at the weird example. We already said that in this reaction with acetone, water, and catalytic acid, that we could form the hydrate. However, previously I said that this was about 0.1%, something like that, way less than 1%. All right. However, let's imagine the following. This is perfluorinated acetone. Do you think this is going to form a lot more of a hydrate? Yeah, absolutely. So this actually forms 99.9% hydrate, even though it's a ketone. And why is that again? Yeah, they're the most electronegative element. So they're going to tug electron density away from that central carbon through dipole induction, right? Which means that this carbon right here is really electrophilic. We know in acetone it doesn't have any really strong electronegative atoms attached to those carbons. It just has hydrogens, so you're not going to see the same tug of electron density. Does that make sense? Yeah?
Is that still true under basic conditions?
Yes, it would still be true under basic or acidic conditions. Yeah, because of that electron density tug, you're really amping up that carbon as an electrophile. Yeah?
That mechanism that we just went over, that only works for the ketones that have fluorine, not.
So the mechanisms we showed above will work for any of these equilibriums, including this one. The difference is which side of the equilibrium is favored, right? So in this top reaction, this right-hand side, yeah, we might make a trace amount of it, but it's going to be pretty negligible in solution. However, we could still show a full electron pushing to get there, right? So it's important to remember that it's equilibrium conditions. Yeah. Good question. All right, so now let's take a look at other oxygen nucleophiles rather than just reacting things with water. And these are kind of along the same vein. However, this time we're going to react with 2 equivalents of alcohol. So that 2 just means we need 2 equivalents. And we're going to treat this with catalytic acid normally. And after this reaction is all done with the arrow pushing, you're actually going to form basically 2 ether type substituents coming off that central carbon. And you're going to kick off water as a leaving group. So you start out with an aldehyde or a ketone. And if you react this with an aldehyde, the final product that you're going to make, meaning the thing with both oxygens attached, is referred to as an acetal. That's the product of aldehydes having alcohols added in. And then for ketones, if alcohols add in, these are called Ketals. So it does depend on the situation. Does that make sense? All right, so the acid, like I said before, we need to be careful with the acid that we pick. So the acid that we normally use here is going to be sulfuric acid, phosphoric acid, toslic acid, or some other acid where the conjugate base is super duper bulky. Toslic acid, some of you might not be super familiar with. It looks like this, and you can imagine when this proton comes off, the negative charge is highly resonance stabilized across all 3 of the oxygens. Therefore, it's a really crummy nucleophile, although it's a pretty good organic acid. So you might see these used as your acid source, either in the textbook or in other problems. Make sense? All right. So let's take a look at the mechanism. This one gets a bit more involved. right. So we'll just stick with simple acetone. It's easy enough to work with. And we're going to use 2 equivalents of methanol. And I'm just going to show my catalytic acid as H plus with brackets, but like I said, it could be sulfuric acid, whatever, as long as the conjugate base isn't good. All right, first step. We need to do acid-base chemistry. We have options, right? We could protonate methanol, we could protonate the ketone, but which one's going to take us in some sort of useful direction? Yeah, protonate the ketone. If we protonate the methanol, that does occur in solution. It just doesn't lead to anything useful happening, so it's not even worth showing in this case. All right, so now we've got our protonated carbonyl. We've got our methanol, and in fact, I'm going to draw them out separately now. Let's kind of break them apart. We know that methanol has oxygens with lone pairs. Lone pairs are decent nucleophiles. So we can show this attacking in, kicking up electron density. All right, so we're getting somewhere. We've got methanol added in, but that oxygen has a positive charge on that methanol, right? We didn't get rid of that proton yet. And we also have methanol floating around, right? All right, what I'm going to do next is something to make our lives a bit easier. I'm going to write plus minus H plus. So what the heck does that mean? Yep, so we're going to deprotonate something and then reprotonate something else. So really it's just saying we're going to move a proton around in this. Okay, so if we do that, I'm going to move the proton from the methanol over to the alcohol. Let me slide this over a smidge. Does that make sense? So this proton, we're moving it over to one of the other ones. In fact, let me show the individual protons. Yeah, that's a good question. So I heard somebody say how. How is this proton being plucked off and then delivered somewhere else? What do you think's doing that?
The other methyl hydroxide is giving up its proton.
Yeah, so methanol is a weak base. It could, in theory, deprotonate this position over here. Then you'd have protonated methanol, which is a good acid, and it could protonate over here. So under equilibrium conditions, some of this will happen, right? The question is why? Why is this a useful step forward? Water is a good leaving group. All right, but then people will often point out and they'll say, well, what about this? This is a good leaving group too. Why can't we just kick that off? We could, and then we'd just be going backwards in our equilibrium, not forward. So both are possible leaving groups. However, by turning water into a good leaving group, we can go somewhere new and different, right? All right, so in the next step, we've got this really, really good leaving group. The question is, what happens to it? So do you think methanol, in this case, is very likely going to do an SN2 type reaction? No, not very likely. So we've got some options, and I've seen this done a couple different ways. Rather than an SN2 substitution, we could almost have an SN1 style substitution. So we could show this kind of popping off. And why is this somewhat stable? It's got resonance, right? So let's draw the resonance structure. All right. So we've got this resonance stabilized intermediate. Yeah. Oh, yeah. There we go. All right, so we also have water floating around. And we also have our other equivalent of methanol floating around, both of which can act as pretty good nucleophiles, right? They've got lone pairs. Do you think we're going to add water back in? No, otherwise we're just going one step backwards in our equilibrium. We're not going anywhere new. So the only thing that really makes sense to show would be forward progress, where this methanol can attack the carbon. It doesn't really matter which resonance structure you choose to show. It can attack either. And in this case, oxygen has that positive charge, so it's perfectly fine accepting a weak nucleophile. All right, so we're making progress. Sorry, I'm trying to squeeze all this in here. Let me slide this over just to make it look a little prettier. All right, what do you think happens in the very last step? Deprotonation. So in this case, best available base. It's going to be the water floating around in solution. And we've regenerated our acid here, right? So at the end of the equilibrium, we spit out water and acid. We know water and acid, when they're around one another, will form the hydronium ion. So in this case, water is technically a byproduct. However, if you've got acid around, it'll react with that. So another way of thinking about this is the same thing as writing H plus H2O. So either one's fine with me. Does that make sense? Pretty steppy mechanism, I will say, but it is important to remember each individual step and why you're doing each individual step. All right, so let's make a note here about the reaction. I'm just going to fill it in this little nook. So equilibrium position depends on concentration of water and or alcohol. So like I said before, we can use Le Chatelier's principle to our advantage here. So if we want to form as much of our ketal as possible, what would be best in terms of water and alcohol? Lots of alcohol. What about water? As little as possible, even better than as little as possible? Let's remove it, right? So actively remove it as the water is being made, and you can actually push this equilibrium along. In fact, there's special glassware that allows for that. There's a piece of glassware called the Dean-Stark trap, where you can actually distill off the water because it has a different boiling point than your ketal and drive this equilibrium towards going further and further and further. They're not super expensive. They've been around for a long time, but yeah, we'll talk more about things like that. Dean-Stark traps are often used for transesterification reactions or converting carboxylic acids to esters too. Yep?
So for this reaction, the reactivity between the aldehyde and ketone doesn't really matter as long as you don't have alcohol in it?
Yeah, both of them can do this. However, aldehydes will readily do this. Ketones you typically have to push on a bit more. Yeah, good question. All right, let's try a harder one. All right, so let's take a look at this one. All right, in this one, instead of having two equivalents of alcohol, we just have a diol. All right, but same idea, we need catalytic acid of some sort. Just like before, we're going to protonate the carbonyl. Yep.
So will neither of these acetals and ketones won't work with the basic, like the basic?
That's a good question. Normally, these are done under acidic conditions just for ease of the reactivity. suppose you could do some of these under basic conditions. However, you might run into side reactions. So normally these are done with acidic conditions. All right, so now we've protonated our ketone. Does anybody remember the name of this diol? So you could call it 1,2-ethane diol. However, it's most commonly referred to as ethylene glycol. So it's one of the weird ones. Common industrial reagent. Next step, one of these alcohol groups can attack in. Doesn't matter which one at all. They're symmetric. All right, and just like we did before, we're going to shuttle this proton over to the alcohol side, right? So I'm just going to shorthand that as plus and minus H plus. You're welcome to do that on mechanisms too, just to save time, because it does get really steppy showing individual proton transfers. Yep?
So why does it go to one alcohol not the other?
What do you mean one alcohol? Oh, I see what you're saying. So let me write it out first. All right, so your question was, why didn't the proton end up over on that alcohol? That's a good question. So if that alcohol were to fall off as water, so meaning if we were to protonate it and if it were to fall off, would that lead to a stable intermediate? No, not at all. Versus where we put the proton that I highlighted, that leads to a resonance stabilized intermediate, right? So we always want to try to form the most stable intermediate possible. That's going to be the more favorable reaction pathway.
So in solution, though, it could go on that one, it just wouldn't go anywhere.
Yeah, in solution, yeah, that would occur in equilibrium. It just wouldn't lead to very much forward progress. Okay, so you can show the next step one of two ways. You can either just show this falling off in one step, or you can show this kind of two-step getting shoved off. I'm fine with it either way. Whoops. All right, and then we kicked off water as our leaving group, right? Because we know water is an excellent leaving group. When it falls off, it's neutral. All right, and the next step, this is essentially going to zip up and attack itself. So you form this weird cyclic ring system. Let me clean this up a bit. All right, and then in the next step, we're just going to deprotonate to get to our final product. Does that make sense? It's a really similar reactivity to what we saw before, but instead of having two separate alcohols attacking in, it's one diol, and it's attacking itself through an intramolecular reaction. All right? So when we look at our final product here, this would be a cyclic ketal or acetal. Right? There's an important intermediate, though, that I did want to take a look at. So let's go back up and look at our other neutral organic intermediate that we formed. This intermediate's not neutral. This one's not neutral. This one's not neutral. Oh, shoot, I didn't do this the way I should have. Well, the organic intermediate in between here, I really kind of messed this up. I apologize. Let's imagine the organic intermediate in between here, right? I'm going to piss Ian off. I can already feel him like looking at me. All right, so can you guys imagine this as being like an intermediate in between there? So once we pluck off the proton, but before it's delivered to the other site, this would be our neutral organic intermediate. This is called a hemi-acetal or a hemi-ketal. So you might hear this a lot, especially in biochemistry. In particular, going back to our pod, we had a polyol, meaning a bunch of different alcohols, so pretty similar to this. But we only had one alcohol attack in, not two. So glucose, by definition, would be what in its ring close form? Would it be a hemiacetal or hemiketal? Hemiacetal, because it started out as an aldehyde. The product you made in your problem of the day only had one alcohol add-in, so it'd be a hemiacetal, not a hemiketal. So in certain situations, you will stop at that. In others, you'll continue on to form your ketal or your cyclic ketal or whatever you're trying to make. Yep.
What are ways to make it stop there and not go on?
Yeah, that's a good question. So why did we stop with glucose at the ring close form? Getting back to the explanation, we made a 6-membered ring. That was really, really stable. So why continue reacting if you don't have to, right? So it depends a lot on thermodynamics. If you form a really stable hemiacetal or hemiketal, it might just stop there and not continue on. Yep, great questions. Sorry about that. All right, so looking back on this, people will stop and say, why? Why do any of this? This seems like a lot of work, a lot of arrow pushing. Let's think about it this way. Okay, so let's say I've got this ketone. And I've got this diol. And during this reaction, I remove water. Therefore, I'm driving the reaction completely to the right. Oftentimes, you'll see this written out as minus H2O in brackets, meaning it's being removed from solution. Therefore, the equilibrium is no longer in equilibrium. It's just being pushed completely to the product side. And we've got catalytic acid around like this. We can go ahead and we can make that exact same product. Oh, I'm having a hard time drawing the rings right. All right. I don't need to include water as a byproduct in this situation because I'm already indicating that we're removing it during the reaction process. Yep.
So if we don't indicate the minus H2O, then we have to have equilibrium arrows?
Yeah, if you don't indicate minus H2O, you can assume it's under equilibrium conditions. Yeah, great question. All right. So you look at this and you're like, okay, why is this useful? Well, let's consider the opposite reaction. Let's say I've got a cyclic ketal and I want to go back to a ketone. What should I do? Flood it with water, absolutely. So in this situation, what I would do is add excess water, right? And catalytic acid. And you can actually accomplish the reverse reaction. So we're just playing around with the Chatelier's principle at this point. Cool thing with this, in my opinion, is up here at this point, this does not have the same reactivity as a normal ketone or an aldehyde. It's no longer really an electrophile at all. It's completely tied up. So what does that mean? We can use this as a protecting group. Is it going to what? So this is I'm not even going to re-ask it. All right, protected ketone or aldehyde that we can remove by changing the reaction conditions. All right, so let's see why this might be useful. All right. So let's say I have this molecule right here. And my goal is to convert this molecule to the following. So it looks to me like what we're doing in this reaction is we're reducing this ester. How do we normally reduce an ester? To an alcohol. Not PCC. PCC is an oxidant. So that'd be the other direction. LAH or sodium borohydride? Or does it matter? LAH. We need LAH. What's the problem with using LAH here? It's going to reduce the ketone as well. So LAH would react with both carbonyls. We can't use LAH here. All right? So we got to get clever. So as a chemist, I would say, well, we've got to protect our ketone. So how are we going to protect our ketone? Well, we just saw how to do that. We can say we need ethylene glycol. Let me make this arrow a bit bigger. We need acid that is catalytic. And we should try to remove water from the reaction mixture. All right, when we do this, the ester is not going to form that ketal. Esters just don't. So not too bad at this point. And then we can go ahead and use lithium aluminum hydride. That's not going to react with the ketal, or cyclic ketal. That's just going to stay put. However, it will reduce that ester that's exposed. Yep?
Would the water in the second step of that start to reverse the ketal?
So you could theoretically skip that second step. However, in our next step, we're going to try to reduce it anyways. Or sorry, get rid of the ketal. Does that make sense?
Well, yeah, that's what I mean. So,
yeah, so even if some of this is removed, we're ultimately trying to remove that in the end anyways. So if you wanted to, you could leave out that second water step. And then in this last step, just say, all right, we need water and we need some sort of catalytic acid in order to remove that ketal. So it's a pretty clever way of protecting carbonyls, specifically aldehydes and ketones that you don't want to react, while you're reacting other carbonyl groups like esters or carboxylic acids, things like that. Make sense? So a little bit tricky. All right. So what I'm going to do, I'll send out an email. I don't think we're going to get far enough for you to do the next pod, the assigned pod. So we'll start our next part of lecture, but that pod will be due the following Monday. So I'll go into Canvas and send out an email. We haven't quite gotten very far into nitrogen nucleophiles, but I think what we'll do is we'll just stop here right now. If you want to read ahead in the book, go for it. But yeah, let's just stop here before we get into nitrogen nucleophiles.